Thank you. So I slightly changed the title to Twistor Amplitudes and Color Kinematics Duality. I was running out of time, so I sort of prepared a gong show talk, which is fair because actually it's based on this paper, which is kind of a short paper. Also, probably some of you have seen parts of this talk. So if that's the case, I apologize. But I think some of you actually haven't. So I'll try to go through most of the main results of this paper. Okay. So the title of the talk is Twistor Amplitudes. So why should we care about Twistor Amplitudes? Well, there are a couple of historical reasons. Well, the first and probably the most important reason in the context of the talk is that Twistor space historically provided a compact construction of nonlinear backgrounds in general relativity. Okay, so this is based on Penrose's nonlinear graviton idea. If you can see that the self-dual components of Einstein equations have actually a linear form, and they exhibit certain integrability properties. So this was originally thought to be a path towards quantum gravity. Nowadays, we understand that it fails in certain regimes, but the idea of reconstructing self-dual backgrounds is actually very powerful, as you will see. And of course, in connection to scattering amplitudes, there is also the construction done by Witten in 2004, which basically introduced the notion of the Twistor transform of the amplitude. Okay, so after the Twistor transform, the amplitude of gluon scattering exhibits novel features. So this was one of the starting points to derive the Youngian symmetry, and it sparked all these breakthrough developments that came in the following years, and that we probably all know. But these two ideas actually pinpoint that there is some deeper interrelation between Twistor theory, scattering amplitudes, and classical GR solutions. And this is especially relevant in the context of recent developments in scattering amplitudes, which aim to tackle the gravitational wave problem. Okay, so there is this sort of nice interplay between Twistor theory, scattering amplitudes, and classical solutions. Okay, so those are historical points, but more recently, we have observed that Twistor variables appear to provide a novel realization of an infinite dimensional symmetry that was found in this work in collaboration with people at Harvard. That pertains to the self-dual sector of massless scattering. So we can discuss that later, but roughly we would think of MHB amplitudes, but it's also holds at loop level. So it's actually a powerful constraint on these amplitudes. And the way that the symmetry was derived was following the celestial holography dictionary. So in this case, you would construct your favorite scattering amplitude of massless particles in the bulk, and then you would map it to the celestial sphere by doing what is called the Mellin transform. Okay, so after you do this Mellin transform, essentially what you do is you go from momentum space basis, like from plane wave basis, to a conformal basis that's given in terms of coordinates on your sphere. We call it seed and seed bar. You trade your energy by a conformal weight, and the spin j is just a discrete variable, which is the helicity of your particle. Okay, so this can be scalars, gluons, or gravitons. Okay, so once you have your amplitude in this Mellin basis, which you can interpret as, conformal correlation functions, essentially because the Lorentz group becomes SL2C, and SL2C is a conformal group for the sphere. Once you have this amplitude, then the action of the symmetry actually becomes explicit, but still is quite complicated. So essentially, we have these generators W, Q, and N, and we act on the scattering amplitude. And then there is some series, there is some finite sum that has to do with taking descendants in the conformal theory. Okay, so these are, roughly speaking, descendants of your conformal primaries, which are these vertex operators that go into the scattering amplitude. Okay, so you need to write it down in this conformal basis because there's explicit dependence on the conformal wave rather than in the energy. But you can check that the first so here Q goes is actually an infinite family of generators. The first 3 generators actually generate Poincare symmetry. Okay, so 3 halves we'll see in a second that corresponds to translation generator, and 2 corresponds to rotations, or sorry, Lorentz transformations. So these first components of this infinite dimensional algebra are actually the global Poincare transformations, but it has much more, right? So it keeps going, and there's still a question of what's the interpretation of the higher modes. Okay, so just keep in mind that here N, which are these modes, are bounded between Q minus 1 and 1 minus Q. Okay, so what's the algebra of this thing? So the algebra happens to be an infinite dimensional extension of Poincare, as I said, and we call it, actually was historically dubbed in connection to higher spins. It was called the W 1 plus infinity algebra. The one actually corresponds to a central term, which is the first mode. The structure constants of this algebra actually have some resemblance to the kinematic algebra, which you may or may not be familiar for the self-dual sector. They are actually modes of those kinematic structure constants. So actually, it's a particular mode decomposition of the kinematic algebra. Okay, so this algebra actually pops up in many different contexts. It first appeared in the context of higher spin massless particles as an extension of SL2C conformal symmetry. It also popped up in n equals 2 superstring, and then more relatedly to this context, it appeared as a symmetry of the self-dual gravity. Okay, both in the classical and quantum setups. Okay, so in our context, it's a symmetry of the self-dual sector, and the important thing to keep in mind is that these generators are can be explicitly related to plus helicity gravitons. Okay, so I'm not going to give you the exact correspondence, but after you have plus helicity graviton amplitudes, essentially you can derive this symmetry from collinear limits. So they are essentially what we call soft gravitons, or higher generalizations of the soft graviton, in the sense that they correspond to subleading orders in the soft expansion. So we can take this construction, actually repeat it for soft gluons, and what we find is a different algebra. It's also infinite dimensional, but the difference is that the structure constants have been turned into color factors now. So instead of having these kinematic structure constants, we now have essentially the color structure constants, and this is just an avatar of the color kinematics correspondence. And if you want to see where it comes from, well, you have to go through all this construction of the generators from soft gravitons and gluons, but it essentially comes from the double copy of the 3-point amplitude. So essentially, these collinear limits are nothing but OPEs, and the fact that the collinear limit is controlled by a 3-point amplitude essentially maps the structure constants from one to another. Okay, so there are two different infinite dimensional algebras. This one is an extension of SUN, and this one is an extension of Poincaré. Most of this talk is going to concern relation to classical spacetimes, and that's why from now on I'm just going to discuss this particular algebra. Okay, so this is what we call W1 plus infinity. Okay, so what are Twistor amplitudes really? So we then define Twistor amplitudes in 2,2 space. We found that actually that can be pushed forward, and essentially you can construct all let's say in the context of gravitational wave physics, actually we believe that 2,2 space is actually quite nice, because essentially all the modes are radiative modes. Okay, so all modes are radiative modes, and because of that, it's actually interesting to make that connection into 2,2 space. I'm not gonna discuss exactly how these classical solutions look in 2,2, but I'm actually going to refer you to papers. One is by this Monteiro paper with Donald and the Rupp, and there's also a recent paper that we put out with Crowley, Miller, and Strominger. Okay, so this discusses the relevance of 2,2 in relation to classical spacetimes. Okay, but in relation to Twistor space is nice in 2,2 because Twistor variables are real, so they live in RP3. And the way you define these Twistor variables is essentially by a half Fourier transform. So you take your momentum space amplitude with lambda tilde variables, and you just Fourier transform your favorite one. So usually you would correlate this with the helicity. In this case, it doesn't really matter. But usually you would transform lambda tilde if your amplitude is negative helicity, and the other way around. So the only subtle point here, as opposed to Witten 04 construction, is that there is we observed that there is an important symmetry of 2,2, which is actually time reversal. And time reversal is a C2 symmetry, but it happens to be a connected symmetry rather than a discrete Lorentz symmetry. Okay, so this means that essentially you have this symmetry built in the 2,2 amplitudes, and you need to mod out by it. This is an important point, because if you don't mod out, essentially you don't have a definition of energy, right? Because there is time reversal symmetry, so your energy can change sign just by doing a rotation, and that's not good if you want to define incoming or outgoing particles. So it's important to actually supplement this construction by modding out the Fourier transform. Actually, this is hard to. Okay, so once you do that, you find that actually this very complicated looking symmetry that I showed you a couple of slides ago becomes sort of trivial. And by trivial, I mean that it can be written down in a single line. Okay, so now for this twistor amplitude, the way this W act is just by some sort of Poisson bracket. Okay, so these W generators are essentially homogeneous functions in mu. So mu is your is the second component of the twistor, and essentially you have these homogeneous functions in mu, and you just Poisson bracket them with your amplitude. And this is just a trivial Poisson structure. And then you can see, thanks to this nice paper, that it matches the previous algebra, which was, you know, couple lines long. So that's very nice. And this realization was known actually from a long time ago. It was just not connected to amplitudes. People knew that the realization of W symmetry had to do with Poisson brackets and Poisson structure, but it was not applied directly to massless scattering amplitudes. Okay, so the first example, which is a very trivial case, is the 3/2 case. So remember, P here goes from 1. 1 is a central term, so it's really trivial. Then there's translations, and then there is SL to C, and then it just keeps going. So the translation case is just very simple to check. If you just write down the 3/2 case, so you replace P by 3/2, essentially what you get is, under the Poisson structure, is that this guy acts as a derivative in mu space. And that's consistent because you know, translations in momentum space are given by lambda tilde, and once you Fourier transform one of them, they essentially become differential operators. Okay. So these are the usual translation generators that Witten defined in his 04 paper. Actually, in these variables, it's remarkable that conformal symmetry actually becomes just a differential operator. Okay. So I would now like to introduce a connection to classical spacetimes. And the idea is that on one side of the connection, there's a classical double copy, which is originally called Kershil double copy. And on the other side of the connection, there is the standard quantum field theory double copy. And so far, in all these years, it hasn't really been clear to me what's the relation between these two, and how to extend the notion of classical double copy to solutions which are not exactly of Kershil form. One step forward was taken in this nice series of papers, where they observed that the classical sort of Kershil double copy had a twistor space analog. Okay, and this twistor space analog to make the connection between spacetimes and twistor functions. Okay, let me just write the spacetimes and twistor functions. The Penrose transform was employed. So the Penrose transform is essentially a map from twistor space. So you take some twistor function, and there is a particular contour integral that maps it to a space-time function. Okay, so to explain it, let me just be more precise here. So we have some space-time coordinate x, and what we do is we take our twistor function, and we so the twistor has a split in terms of lambda and mu, right? We essentially set mu to satisfy the incidence relation. So mu now becomes, okay, let me just write it in indices. Mu now becomes correlated to lambda. Okay. So after you impose the incidence relation, what you have is essentially a function of lambda, and then you do a contour integral on actually it's RP1. So this contour integral picks up some poles, and if the function has no poles, and there is no space-time correspondence. But for functions which are meromorphic, you will find that the poles essentially contain all the information of the space-time singularities. Okay. So if you want to look into that in more detail, there's this nice paper, and there is also well, my paper from last year. Now, after we have these Twistor functions, we can do three things with them. We can turn it into a Bile tensor, we can turn it into a field strength, or we can turn it into a scalar function. Okay, so these are schematically, I mean, these are roughly speaking related via the double copy, and I'll show you how in a second. But just to keep the notation straight, we define this sort of self-dual component of the Bile tensor by taking the Lorentz index Bile tensor, and we hit it with Pauli matrices, which essentially extract the self-dual part. And we do the same with the field strength. And so there is this sort of notion that the Bile tensor, because it's a helicity 2, can be written as a square of the field strength tensor, right? In these variables. So morally speaking, is some relation of the sort of, and you have to totally symmetrize these indices. Okay. So another question is, how does this double copy operate in Twistor space? Now, to answer that question, I'm gonna refer to a single particular example. I don't claim that I know the answer for general amplitudes, but in the case of the 3-point amplitude, it's very explicit that there is a derivation of the Kerr-Child double copy from the 3-point double copy of massless amplitudes. So I'm just going to cover that part, and then I'm going to comment on how to extend it to higher points. Okay, so this is the Kerr example, and I'm going to briefly review what we did in 2018 with these amplitudes and how they double copy. So we started with some amplitude which have a massive particle of higher spin, which essentially we took to infinity, and some massive momenta, which is classical. And the amplitude happens to exponentiate after you take the so-called minimal coupling. Okay, so if you write it in terms of this Pauli-Lubansky operator, so the Pauli-Lubansky operator is given by some sort of dual of your spin vector. And you have some momentum transfer K, and then essentially this operator exponentiates. So that's one of the main results of me and some collaborators. And what was found later is that actually you can take this amplitude and add some sort of knot charge. Okay, and this will be especially relevant in connection to Twistor space. So the way you add this, you add this knot charge is essentially you have some mass here. So mass you can think of as the coupling constant. So there's some, roughly speaking, this h by g. So there's a coupling constant, and essentially you do some electromagnetic rotation. Sorry, some electromagnetic duality rotation, and what you get is essentially a theta angle. Okay, so this you can think of being the theta term in the case of gauge theory. In the case of gravity, it has some other interpretation in terms of a knot parameter. Okay, so after that, you can essentially rewrite the coupling into real and imaginary parts. This one we call the not charge. And this one is just the real mass, okay? So there's some kappas and so on. Now, what happens is that this discussion was done essentially in 3,1. So if we want to analytically continue that discussion, actually what happens is that the not charge and the spin will rotate. Okay, so let me just write for you the 2,2 amplitude. And once you analytically continue, essentially you will rotate the spin and the not parameter. So that's the 2,2 3-point amplitude for gravity. Okay, and now you can ask about the same amplitude for gauge theory, also in the minimal coupling regime. And you'll find that, of course, it goes with the coupling constant. And then instead of having the mass, you would have some electric charge. And instead of having the not charge, you would have some magnetic charge. But all the spin dependence will be the same. So, oh, actually, let me just consider both signs here, so you know what's the difference. So the difference between two helicities is roughly given by this coupling constant, which is parity odd now. So if I flip helicity, I flip the sign of the magnetic term. And also because the spin is a pseudo vector, it also flips helicity flips sign under a parity transformation, right? So that's why this sign happens to be important. But now you can see that in 2,2 space, you can get solutions in which one of the helicities decouple. Okay, so that means that 2,2 space admits real self-dual solutions. Okay, and that just means that one of the helicities will vanish. I mean, will not couple to a source. Okay, so this was known. In the context of tau-NUT solutions. If you go to the self-dual point, tau-NUT spacetimes are necessarily complex, but in 2,2 signature, they actually admit a real embedding. So this was especially important in the context of the quantum gravity path integral, because this act as saddle points. Okay. So so now you may ask, how does double copy operate? Well, double copy operates in a sort of trivial fashion, because if we call this the graviton amplitude, and this we call the gluon amplitude, essentially what you have is this sort of relation, that the graviton amplitude is the square of the gluon amplitude, but you need to impose a condition on the spin vector, right? Because here you will have an exponential of A, which is a spin vector acting on this source. And here you will also have an exponential, say, of A prime, which is a spin vector acting on this source. Now, what we find is that A, regarded as an operator, admits admits a direct sum structure. So essentially, what you can see is that if you exponentiate these two terms, you can consider A plus A prime as the total spin. Okay, and this total spin happens to act on the massive source, which is obtained as the double copy of the gauge theory source. Okay, so essentially, what's at play here is the massless double copy acting on the graviton, regarded as the double copy of the gluon, but also the massive double copy on the source, which have a spin A or A prime, and it would give a spin A plus M prime as the total spin. Okay, so this constrains the structure of the amplitude a lot, because you can see that if the amplitude was not an exponential, essentially this sort of massive double copy wouldn't have worked, right? So the general form of the amplitude is actually a power series in the spin vector. It's not guaranteed at all that once you have an arbitrary power series of the spin vector, you multiply that by a different power series with a different spin vector, that's going to be a function of the sum, right? So this is a very particular structure which appears for minimal coupling, okay? But it's not true away from minimal coupling. So once you have this structure, essentially what you can do is that you can twist or transform. So let me just do that for you. I'm gonna take, actually any helicity will work, but let's just stick with the graviton case. So I'm gonna compute the amplitude in Twistor space for a graviton by Fourier transforming my momentum space amplitude. Okay, and then you're gonna see why it's important to mod out this by the symmetry. So this symmetry, what it essentially means is that if I expand mu as some sort of a scale times some projective spinner, the mod out just means that I'm going to integrate over the positive region of that scale. Okay, so this projective component lives on RP1, so and I integrate over my positive region, and then I just expand the amplitude. So you can see that when I expand my amplitude, sorry, yes, small variable notation problem. What's going to happen is that if I have an exponential structure here, what I'm going to get is a shift in this Twistor amplitude. Okay, so for the case of gravity with a spin, I'm going to get something that goes like a lambda, which is a variable, and then lambda tilde, which I just replaced with eta omega. And then essentially what's going to happen is that this is going to act as a shift of my Twistor variable. And so you can see that the Twistor space function for care is going to have the spin acting as a shift. I'm just gonna resolve the integral now, and I'm just gonna explain the answer. But actually, you can do it. And it's quite trivial to do it. So the answer in Twistor space essentially goes like x plus a. There is a momentum direction. The way this momentum direction appears is because there is a delta function, which is essentially momentum conservation of this 3-point amplitude. And there is some coupling constant, which is by G. And if you have not charged, then there is like n plus n upstairs. Okay, so that's essentially the answer for the Twistor space function. Now, one thing that becomes especially important is that the Twistor space function has poles, okay, and the poles of the Twistor space function have a very intrinsic geometrical meaning if we do a Penrose transform, right? So if you plug this into the Penrose transform, what you can see is that whenever this Twistor space function has a pole, the location of the pole is going to act as a null vector of the Penrose transform. So suppose that this function has a pole at lambda eta equal to eta. Okay. So suppose this function has some structure like that. You can easily check that eta is going to act as a null vector of your Weil tensor after you integrate and deform the contour on the real line. So this means that every pole of this function, of the Twistor function, actually corresponds to what we call principal null direction. Okay, so principal null directions are null eigenvectors of the Weil spinor. And you can count how many poles you have, and you can see how many principal null directions you have. So here, for instance, we have 2 poles. We would usually, if you have a quadratic form in the numerator, what we do is we write it in terms of its 2 roots. So it has 2 roots. One of those roots I can call eta, and the other one I can call mu, right? So mu and eta are essentially related to this operator by just looking at this in projected coordinates and computing its roots. Okay, and so you can see that for this particular amplitude, we have 2 principal null directions, and that means that the resulting Weil tensor, which we call CAVCD, is of type D. Okay, so type D essentially just means that it has 2 principal null directions. Okay, but type D spacetimes are very particular in the sense that they admit a decomposition in terms of Kerr-Schill coordinates, right? So every time you have some Weil tensor which has 2 principal null directions, you can always write it as the square. Like if you group its principal null directions, you can always write it as a square of a spin 1 curvature. So that's essentially the same as saying that the Weil tensor just double copies from spin 1 curvature. And just to make it explicit here, if you have these 2 principal null directions being mu and eta, essentially what you get is this decomposition, right? With some constant factor. Okay. So this is the so-called bi-level copy. And there's also a realization of the bi-level copy in terms of the metric itself, which is related to the Kerr-Schill double copy. But in its most gauge invariant form, it's actually given by gauge invariant quantities, right? If we actually want to write the double copy structure in the Kerr-Schill form, that means we're choosing a particular gauge. So it's not extremely clear how to relate that to on-shell amplitudes. Whereas in the case of the Weil double copy, because it's given in terms of gauge invariant quantities, it suggests very strongly that there is a relation to the amplitude double copy. And in fact, we will see now that that's the case. So going back to the momentum space double copy, what we knew from very early considerations is that the 3-point amplitude for plus or minus solidity gravitons happens to be the square of 3-point amplitude for gluons, right? And in fact, this is the case because if you look at the scalar amplitude, which you can define just as a coupling constant, and you can rescale that coupling constant, the scalar amplitude is just 1. But if you were to plug it formally in the KLT relations, essentially you would divide by the scalar amplitude, which is the biadjoint kernel. So this sort of relation is the simplest avatar of the KLT construction, and it actually happens to be explicitly realized in Twistor space. So if you do your Twistor space transform, what you find is that the Twistor amplitude for, let's say, helicity H actually scales as 2H. So if you have, let's start with the previous case. If you have gravity, then you get a cube factor. You have n plus n, and you have g, some square root of g. So this is for gravity. If you do the Twistor transform for Young-Mills, you get the coupling constant and you get E plus G. Downstairs, because you have different helicity, essentially by power counting, you will find that it's actually a square. And if you do it for scalars, essentially you will find a simple pole. Okay. So you can sort of see that because of this exponential structure, the exponential structure as this sort of shift, the double copy in momentum space is precisely preserved after you Twistor transform. So you can write the same relation now just for the Twistor amplitudes. And then plugging this relation in the Twistor transform actually is the same as the bi-double copy. So what we have seen in this very short experiment is that due to the exponential structure, what you find at the end of the day is that the momentum space double copy is preserved under the Twistor transform. And that provides sort of underlying reason for the bi-double copy to hold, except that now you can actually push it forward and you can compute the Twistor transform higher point amplitudes, not just 3-point amplitudes, where this relation sort of breaks down. Okay, so this is a very particular relation for 3-point amplitudes. If you push it to higher points, of course, there is a KLT kernel, and so the structure essentially breaks down, but that's expected because on the gravity side, we know that the Kerr-Shield double copy only holds, or so far we only know we only know examples for stationary solutions, which correspond to these 3-point amplitudes. So so that provides some sort of prospective extension of the classical double copy that I'm currently looking into with some colleagues. So I guess I'm just gonna leave time for questions. So that's all that I wanted to say for now.
Thank you very much for your talk. Any questions from the audience?
Have you looked? Hi. Have you looked at type N spacetimes in this language? Presumably, there's also something nice in Twistor space.
Right. So type N, by type N you mean rank 1. I only one null degenerate.
Yeah, meaning that all the principal null directions are the same.
Yeah. So that's right. So
in that case, you get PP waves, but you also get something more.
Exactly. Yeah. So that's also a case where the bi-double copy holds, and you can sort of get type N for free if you just degenerate. If you take the limit where mu is degenerate with lambda, that corresponds to a particular deformation of the spin vector, but I haven't really looked into it. But it's sort of interesting that it's contained in this particular limit where essentially, and eta and mu degenerate.
But okay, in that case, you're obtaining, let's say, a particular type n solution. Is that related to the, when you infinitely boost, say, a black hole, then you do get like a type n shock wave. Is that related to this thing you just said, or is it this different story?
Yeah, it's presumably related to the conal boost, but I haven't really looked into it. Yeah, for sure. These are very particular choices of eta and mu. Actually, eta and mu are functions of the space-time here, given by this 2x2 matrix. So yeah, I'm not sure if it's not guaranteed that in general you can obtain all type n solutions, but a rather particular class just follows from adding a deformation to the spin.
Thanks.
Any other questions from the audience?
I have a question. So you mentioned an infinite dimensional extension of Poincare algebra. So the existence of this symmetry is somehow in apparent contradiction with the Coleman-Mandula theorem that prescribed that the symmetry realized by a quantum field theory can be represented as the direct sum of Poincare group and an internal symmetry group, or other some loophole, for example, the existence of, in this case, of a mass gap.
Right. Yeah, there's no mass gap as far as I know. So things work a little bit different in 2,2. I guess that will be my first intuition, that in 2,2 essentially you can decompose space-times into self-dual and anti-self-dual pieces, and they are both real. And so you can regard them as real and independent solutions of the massless wave equation. And so what this W is doing is essentially acting only on the self-dual part. So it's a chiral symmetry. In 1,3, like in Lorentzian signature, W would necessarily act like as a conjugate operation. And so it's not exactly clear what that's probably not a symmetry. Yeah, that's what I want to say. That's probably not a symmetry.
I see. So it's not a symmetry of the S matrix.
Yeah, exactly.
I see.
Thank
you very much.
Sorry, can I just say that the S matrix in the self-dual sector at tree level is 0, and that this, I mean, I've never seen it very explicitly somehow written like this, but I think the argument is that somehow there's too much symmetry for something to exist, and then at one loop there should be some kind of controlled anomaly that gives the all plus amplitudes. So actually, Alfredo, the anomaly of this algebra, I guess this has been looked right at one loop.
Yeah.
And somehow the algebra extends in a quite simple way, but yeah, it would be interesting if that thing was related to the, could be thought of as generating the one loop amplitudes. I don't know if if people have somehow addressed this question. I'm
not sure if the correction is non-trivial. I think that the algebra is quite rigid. Especially because it has this symplectomorphism realization, and if you just look at the one loop amplitude, you will find that it respects the symmetry with the exact same structure constants.
Right. I mean, if you think about it in terms of kinematic algebra, also the loop integrand does have this kinematic algebra, and then you do the loop integral. You have to go off 4 dimensions, and then you get a finite answer, which, well, you get the usual rational result for the all plus amplitudes. And it would be interesting somehow that could come about from the celestial amplitudes, but I don't know what that has been the net loop level for celestial amplitudes, and what about dim reg, and is there some equivalent or?
Yeah. Yeah, that's a good question. I really don't have much more to say on that. That's a